So let's see, 1, 2, 3, 4, 5, 6, 7. Who's missing?
Jonah is missing. Yeah, he is connected now.
Okay, Jonah, here he is. 1, 2, 3, 4, 5, 6, 7,
Thank
8.
you, Professor.
No problem. Okay, so we are almost ready. Just a second. Just 1 second. Okay, let's do a share screen. Okay, so, okay, I hope you're ready for this wonderful lecture that is going to be essentially a lecture about interacting classical gases, cumulant and cluster expansion. All right, so this is going to be the most complicated calculation that we will do.
Help,
I'm
Professor.
going to ask you.
Professor,
Yes?
can
Yes.
you please read for me the headings? I don't understand some words.
Interacting classical gases, cumulant and cluster expansion.
Okay, thank you.
All right. So what I would like you to do in this class is...
Professor,
Yes.
can you hear me?
Yes, I can.
Actually, can you increase your voice somehow? Or
Can I increase my what?
voice? Because,
My voice.
yeah.
Not too much, because I have... Yesterday I had surgery in my mouth and I cannot shout, otherwise I have pain.
I mean, maybe
So just a second. We'll try to do. Can you hear me better now?
Yes, thank you.
Okay. All right. So, so what I wanted to say is, if you have questions, stop me at any time, because the calculations are more complicated than what we had up to now, and therefore you should be able to, you should understand all details. You're supposed to understand all details in order to follow. So this is not something that I typically ask in the final exam. Nevertheless, I invite you to study this subject because it's very important for your own education. So we're going to consider an interacting quantum gas that has an Hamiltonian that is composed of two parts: a non-interacting part and then an interacting one. And interaction depends only on the generalized coordinates in general. So the non-interacting part, Hamiltonian, we will call it H naught. And the interaction part typically is taken as the sum of pairwise interactions among the particles. Two-body interactions, so-called two-body interactions. Okay, so each pair of particles in this sum has an interaction potential V, and of course this sum is taken over all pairs. All right, so our goal is going to be always to compute the equation of state for this for this system. And in order to do so, let us start by computing the partition function. Partition function is Z. In general, the partition function is going to be sum over all dq, dp, h to the 3n n factorial. And then I will have e to the minus beta h naught, e to the minus beta v. All right. So this is equal to what? Let me multiply and divide by the non-interacting partition function.
Professor,
Yes.
is this V the volume or the
Oh yeah,
potential?
sorry. This is not V. Is U. Okay.
Okay.
So let me divide this by integral dq dp over h to the 3n n factorial e to the minus beta h, and then multiply this by integral dq dp h to the 3n n factorial e to the minus beta h naught. Okay? So why did I do this? Because now you see that this object here, I can call it Z naught, is the non-interacting partition function, right? That we already calculated. This object here instead is essentially the average of e to the minus beta u with respect to the non-interacting partition function. So this knot here indicates that the average is taken with respect to the non-interacting partition function. So if you look at what I wrote, this is just a definition of the average, of this average. Okay?
Sorry.
Yes?
I do not understand what you just wrote. You divide by
Well,
e to the
so
minus
what
beta h.
does it mean? What does it mean to average something with respect to the non-interacting partition Hamiltonian? Means to calculate dq dp over h to the 3n n factorial e to the minus beta h naught times this something, and then you have to normalize this by z naught. This is the definition, if you want, of an average with respect to in the canonical ensemble. If I want to average something, to calculate the average magnetization, the average whatever you want in the canonical ensemble, what do? You do this, right? And here I'm looking at this object here, I'm seeing that here there is e to the minus beta h naught times e to the minus beta u. Here there is an h naught, forgot. And therefore, I can reinterpret this writing as the average of e to the minus beta u with respect to the non-interacting Hamiltonian. You agree now? You see?
Yes. I mean, I was just confused because you didn't put h not there.
Okay. Good.
Can you wait a moment? I want to write. Thank you.
Okay, so tell me when I can restart.
Okay, it's fine.
Okay. All right. So let's now, so therefore I can rewrite this as equal to Z naught average e to the minus beta u naught. Okay? And since Z naught is, I know what it is e to the minus beta F naught, where F naught is the non-interacting free energy. Well, then I just have to multiply this by e to the minus beta u, and I obtain my partition function. Now, ideally, you see, what I need to compute is not the partition function. The partition function is not a physical quantity. What is a physical quantity is the logarithm of the partition function. In other words, what we need to compute is F is the free energy, which is minus 1 over beta log of Z, and which is going to be equal to F naught minus 1 over beta, the log of the average of e to the minus beta u naught, right? This is what I need to compute. In other words, what I need to, if I now want to perform a perturbative expansion, what I need to do is expand not just perform an expansion of this object, but perform a perturbative expansion of the log of this. Clear? Because I want to compute the free energy at the end of the day. This is the physical quantity. So let me write it just repeat it. If I now want to use perturbation theory, you all know what is perturbation theory, right? Is when you expand in powers of the interaction. You have done this in quantum mechanics, for example. Right? Have you done it in quantum mechanics? Good. So if I now want to use perturbation theory, I should not use it. I should not expand Z, but F. So let me tell you in other words what this means. If I do perturbation theory for Z, what I would write is the following: e to the minus beta F naught times the perturbative expansion in powers of the interaction of the average. So, which is going to be 1 minus beta average u naught plus beta squared divided by 2 average of u naught squared plus etc., higher order terms. Now, what I'm saying is that this expansion by itself is not meaningful, because what you want to compute physically is not the partition function. So you don't need a partition function written up in series of in a power series in the interaction strength. What you want to compute is the free energy, F. Now, if we perform the same expansion for the free energy, we will get F naught plus, or sorry, minus 1 over beta, the log of 1 minus beta u naught plus beta squared over 2 u naught squared plus etc. etc. Okay? So now you see, in order to have,
Professor?
yes,
So what you said there is no need for Z expansion while we need F. Is it related to the physical meaning or?
yeah, well, it's related to the fact that the partition function by itself does not have physical meaning. Okay?
Oh, okay, okay.
But you also mentioned about the use of a perturbation theory.
Yes.
So can you point out the reason why when we want to use perturbation theory, we should not expand this?
So this is a general statement I'm going to make for you. When you want to do perturbation theory, so what you're trying to do is to compute whatever you want to compute in a power series in a small parameter, which typically is the interaction strength divided by some other energy scale. Okay? So this is what
Yes.
you do. You agree? Now the question is what you should expand. And the answer is you should always write down the power series for physical quantities. And what is a physical quantity? Is a quantity that is measurable. You cannot measure a partition function. You can measure a free energy. Okay? What is physical is not the partition function, is the free energy. So what I mean when I say let's write let's expand the free energy, I mean the following. You should always write the power series relative to perturbation theory for physical quantities, that is, quantities that are measured in experiments. Okay? So at the end of the day, you should aim at constructing the perturbative expansion for those physical quantities. Clear
Yes.
now?
Yes.
Okay. So that's why I'm saying I want to write down a power series in the interaction strength, not for the partition function as I've done in the upper line, as I've done here in 1, but for the free energy as it is done in 2. Now, what is the problem now? You see that when I do it for the free energy, I get log of this. So I have to expand also this logarithm, right, in power series, if I want to write down a power series. And when I expand the log, I have that log of 1 plus x is equal to x minus x squared divided by 2 plus etc., etc., etc. Right? Therefore, when I expand what is written up here, what I get is f naught minus 1 over beta, and then I get x. So what is x? X is this. So I get minus beta times minus beta u naught plus beta squared over 2 u naught squared plus etc., etc. So this is my x. Now, the problem is the following, that here if I keep also this second order term, I will also have a term that is second order interaction in the second order term of the expansion of the log, right? So I have to add that minus 1/2, and then this stuff minus beta u naught plus etc., etc., squared. Okay, so let us now recombine all these terms, keeping all the terms that contain the same power of the interaction together. So what do I get? I get that this is equal to F naught plus, so I had minus 1 over beta times minus beta, which is 1. So plus average of U naught, average of U naught. Okay? Minus beta over 2 times U naught squared. So this is what was coming from this term here. And then I will have minus U naught. What am I doing? Not U naught, it's U squared naught minus average of U naught squared plus higher order terms. Where does this term come from? It comes from the square. You see, from this. Plus higher order terms. All right. So in other words, what I'm discovering is that my partition function can actually be written, if I remember that the partition function is e to the minus beta f, I can actually write my partition function as e to the minus beta f naught minus beta u naught minus plus beta squared over 2 u naught minus u naught squared plus etc. 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 Now, if you look at this, this is exactly like a cumulant, an expansion in cumulants of the cumulant generating function in probability theory. This is the first cumulant of the interaction. This one is the second cumulant of the interaction. And so on and so far. That is why this expansion of the free energy, so essentially what we are doing is an expansion of the free energy. This expansion of the free energy is called the cumulant expansion in the literature. So cumulant okay. Is it clear for everybody?
Yes.
Okay. Excellent. So now what do we do with this? Well, we essentially, so what this tells us is that if you want to compute the expansion for the free energy in power series of the interaction strength, what you have to be able to do is to compute the average with respect to the non-interrupting Hamiltonian of the interaction, of the square of the interaction, and so on and so far. So now let us do this for our physical system. So let us implement it for two-body interaction. All right, so now for two-body interactions, the average, so let us compute the first cumulant, the average of U. Well, this is by definition 1/2 sum over I not equal to J, average of V QI minus QJ. I can actually simplify things and write it as 1/2 sum over the ordered pairs, so without repetitions, VQI minus QJ, simply because I'm assuming that V is a symmetric function of QI minus QJ. Actually, typically the interaction depends on the absolute value of the distance, right? Unless you have some special circumstance. So what I'm assuming is that if I exchange the indices in QI minus QJ, I obtain the same interaction potential. That's why I can actually, I apologize, this 1/2 is not there. That's why I can forget about summing over all pairs and sum over all the other ordered pairs. All right, so now I have to compute this average.
Professor,
Yes,
how is V different from U?
well, so this is what I defined here, right? U is the function of all coordinates, and V is defined, so U is equal to the sum over I and J VQI minus VQJ. Okay?
Okay.
All right. So now this average is what? This is equal to the, let's write it here. This is integral dq dp e to the minus beta h naught times v divided by integral dq dp e to the minus beta h naught. Now you see that when I perform this integration, the integral over dp gives the same result above and below, right? You see that? Because, well, it's going to give us essentially integral over dp to the minus beta h naught, which is p squared over 2m. And therefore, this integral is just normalized out. What I obtain is that this is equal to the sum over I smaller than j integral dqi dqj divided by the normalization, which is just the volume squared of v qi minus qj. Okay?
Sorry, can you repeat? Yes.
Well, what I'm saying is that this average, this one, which is defined in this way, since the integrals over dp, since v is a function of only qi and qj, I can perform directly the integration over all dp's and all dq's apart from qi and qj, and I will obtain the same result in the numerator and in the denominator. Therefore,
Professor, what is
yes,
independent just now?
what is?
Independent. I think you mentioned that the
V is independent on Q, is independent on P. V depends only on Qi and Qj.
I see.
So therefore, I can perform all the integrations over dP and all integrations over dq apart from Qi and Qj. And they give me the same result above and below, right? So therefore, they are normalized out. And what remains is just the integral over dqi and dqj. In the denominator, this will give me the volume squared. In the numerator, this will give me integral dqi dqj of vqi minus qj. All right? Can I move on?
Sorry, Professor.
Sorry?
The B is a volume here. B is it's
I cannot hear you.
B in denominator is volume here, or not?
In the denominator is volume squared.
Oh, how can I get?
How can you get a volume squared? Well, here, when you do this integration, okay, look, let's do this integration here briefly. This is equal to integral dp e to the minus beta h naught and then integral over dq over the product over the over k different from I and j dqk. Sorry, I have to do it somewhere else, otherwise you cannot understand. So let me calculate this average in the next page. So this is what is integral dq1 dqn, integral dp1 dpn, e to the minus beta, sum over I pi squared over 2n, v qi minus qj, divided by the integral dq1 dqn dp1 dpn e to the minus beta sum over I pi squared over 2n. Okay? This is equal to what? Above, so of course, I can rewrite it as integral dp1 dpn e to the minus beta sum over I pi squared over 2n. Then I can integrate over all k such that k is not equal to I or j, dqk, and then I will have integral dqi and dqj of vqi minus qj. Okay? In the denominator, I will have the same, and then in product integral dqi dqj. You agree? You agree with me?
Yes.
Okay, so now this integral is equal to this one, so I can simplify. This one is equal to this one. I can simplify. This one is just equal to the volume squared. And therefore, I obtain that this is equal to integral dqi dqj over volume squared of vqi minus qj. Okay?
Okay, thank you.
No problem. Okay, so now that we understand this, we have this sum. I can now change variables here and introduce the two variables q equal to qi minus qj and big Q equal to qi plus qj divided by 2. Now you see that v depends only on little q, not on big Q. And I leave it to you as an exercise to compute that the Jacobian of this transformation of variables is equal to 1. Therefore, what I get is sum over I and j integral d big Q d little q divided by v squared v qi v little q. Now I can perform the integral over big Q that gives me a volume, and therefore I get sum over I smaller than j of integral dq over v of q. All right, so it's clear that now there is no dependence on I and j anymore because all these integrals are the same, independent on what are the values of I and j. And therefore, this sum I can perform it is equal to the number of ordered pairs that I can construct, which is n times n minus 1 divided by 2 times integral dq over v of q. Okay?
I'm sorry.
Yes?
Why it is n times n minus 1?
Well, it's n times n minus 1.
Yes.
Well, because here I'm taking a sum over all ordered pairs. Now, let me ask you this question. If I have n elements, how many pairs you can construct out of n elements?
N elements.
Yeah, you have n elements in your set. How many pairs you can construct?
It's
N over 2.
Wait a second, let her
on.
n times n minus 1, correct.
Yes.
So this is the total number of pairs. Now, how many ordered pairs? Ordered pairs, it means that the order within the pair doesn't matter. So that Q1 times Q1, Q3 is the same pair as Q3, Q1.
Oh, it's over 2.
Is divided by 2. So this is just a number of ordered pairs. You see?
Yes.
All right, so now that we know this, let us move on and compute the next coefficient. So what is the next coefficient, which is a bit more complicated, is u squared naught minus u naught squared. Now, if you think for a second, this is equal to sum over I smaller than j, sum over k smaller than L, average of V qi minus qj, V qk minus ql naught minus V qi minus qj naught V qk minus ql naught. Okay,
Yes.
okay, so now let us focus on this. So this is equal to the following. If you repeat the same calculation as the one we have done here, so I will not do it because it's obvious, this comes out to be the integral over dq1, dqi, dqj, dqk, dql divided by volume to the fourth power of v qi minus qj, v qk minus ql. Okay? Now, it is evident that if the indices I, j, k, and l are all different, okay, then this is equal to the average of v qi minus qj times the average of v qk minus ql. You agree?
Yes.
Now, this is true also if only two of the indices are equal. For example, if I is equal to k, but j is not equal to l. Also in this case, what I get is that this is equal to this product.
Professor,
Yes.
both of them should have the knot, right?
What?
Both of them should have the knot, or like
Yeah, all of them have the note.
okay.
All of them. Everybody has the note. So the only situation in which this is not equal to the product of the average is if I is equal to k and j is equal to l. In that case, this is not equal to the product of the average, but this is equal to the average of v qi minus qj squared. Okay, so when they are different, then it's always equal to the product of the averages. But when they are equal, pairwise, I is equal to K and J is equal to L, then this is the average of VQI minus QJ squared. Therefore, it's clear that since in all these instances, this is just a product of the average, this is canceled by this minus the product of the averages in all these situations. And the only thing that remains is in this sum is that this is equal to the sum over I and J, when they're pairwise equal, of VQI minus QJ squared minus VQI minus QJ naught squared.
Is that
Yes,
for the first term?
yeah, this is for this one. So from here, you have to go down here. Okay. And this is equal, if you do the calculation, it's exactly as before, to n times n minus 1 divided by 2 is the number of pairs. And then you will have integral dq over v of q squared minus integral dq over vq, everything squared. All right?
Professors,
Yes.
so what you mean is that using the identities you've given us, we can simplify the K and L becomes only I and J, and yeah, and
I
then
is equal to k and j is equal to l. Yes.
I see. So we are taking the third case only, or?
Only the third case. Only this survives. Okay.
Oh, because the other two terms are canceling each other.
Yes, exactly. All right. Can I move on?
Yes, yes.
Okay, so let us now, it's clear that in order to compute this cumulative expansion, the average of u is this integral dq vq. The average of, so this fluctuations will require me to compute the average of vq squared. So let us work out an example. So the example is the following. Take the potential V of Q equal to V naught times e to the minus beta, e to the minus mu times absolute value of Q, right? So this is a potential that decays exponentially on a length scale L, which is 1 over mu. This is the length scale of decay of this potential. So now let us compute the average of U naught. Well, this is n times n minus 1 divided by 2 integral dq over v of q. So let me compute this integral. What I get is the following. This is, since the integral depends on the absolute value of q, I can go to spherical coordinates. I will have a solid angle in d dimensions. And then I will have integral between 0 and plus infinity of q to the power d minus 1 v naught e to the minus mu times q. Well, it's straightforward to do this integral. What you get is omega d times v naught. Then I change variables. I set mu q equal to x. So I will have mu to the power d. And then I will have integral between 0 and plus infinity of x to the power d minus 1 in dx e to the minus x. And this is by definition a gamma function. So this is equal to omega to the power d gamma d and then v naught mu to the d. In other words, if I now, oh, sorry, I apologize. I have to divide everything by the volume. I forgot the volume at all stages. So therefore, at the end of the day, I can rewrite this as omega d gamma d, then v naught, and then L to the power d divided by v, where v is the volume. So I have the ratio of, you see, I have the ratio here. Essentially the ratio of L to the linear size of my system to the power d. L is the typical scale of decay of the interaction. The interaction is decaying exponentially on that scale. Okay?
Yes.
Good. Now, so therefore, what I obtain is that this is equal to, after this integration, n times n minus 1 divided by 2 times omega d times gamma d times v naught times L divided by little l to the power d. So this is the first calculation I had to do. Second calculation,
Can you go to the previous page?
yes.
Professor,
Mm-hmm.
this one is related to the sphere volume in the n dimension you show us before, right?
What do you mean?
I mean, I think we did similar calculation before.
Yeah, this is an integral. It's an integral, it's spherically symmetric integral in d dimensions. That's how you, I mean, if you take mu equal to 0, right? So if you compute this integral for mu equals 0, this is going to be the, well, it's not the integral of, it's not the volume of a sphere because I'm taking the integration all the way to infinity. But yeah, it's similar. It's conceptually similar.
And the d dimension is the dimension for dq?
But is the dimension in which the particles live. So I'm not specifying whether the gas is living in 3 dimensions, 2 dimensions, 1 dimension, or 4 dimensions, or even 5, 6, whatever.
Oh, I mean, because usually you have like dq1 to dqn, but now you have dq, which is the interaction, like dqi and dqj. I'm thinking if that's, I mean, that's the change.
No. This is because I'm always simplifying things, but every one of these guys, dq1 to dqn, every q is the coordinate in space of a single particle. Now, if the physical space is d-dimensional, this is a vector in d dimensions. You see? Every q here is a vector in d dimensions. I'm not writing the signs of vector. I should, but I'm not writing it because I thought we understood. So if I have a gas, I have n coordinates for the particles, n coordinates for the moments of the particles in phase space, and each coordinate is a d-dimensional vector if I'm sitting in d dimensions. Okay? You understand now?
Yes.
Okay. All right. So now, let us now compute u squared, not minus average of u not squared. This was equal to n times n minus 1 divided by 2. No, I don't remember. Yeah. I have integral dq over vq squared minus integral dq over vq squared. Okay? So therefore, I have to compute these squares of these integrals. Well, the first one, integral dq vq squared, is straightforward to compute. Is the same as before. I will get omega d, gamma d, v naught squared, and then L to the power d divided by 2 times the volume. Therefore, you see something interesting. When I take integral dq vq squared minus divided by v minus, sorry, what did I do? I have to divide by the volume, of course. Minus integral dq over v of q squared. What do I get? I get that this is equal to omega d gamma d times v naught squared times L to the power d over 2v naught, 2v, v is the volume, times 1 minus 2 omega d gamma d L d over V. That's because I have a square here, and therefore I will have the square of the ratio of LD to V. Okay?
Sorry. Where does the factor 2 come from in the 2V?
Here,
Yeah, where
well,
is
it comes from the fact that if I have V squared, I will have to integrate dq, q to the power d minus 1, e to the minus 2 mu q, because I'm squaring the potential.
I see, thank you.
All right. And now you see something interesting. I'm assuming that I'm doing a perturbative expansion, and therefore assuming that my gas is a low density gas. What does it mean? It means that, in a sense, the volume that contains the gas is much, much bigger than the how to say, than the reduced volume of the number of particles. In other words, I'm practically assuming that particles can hardly see each other when I go to the thermodynamic limit. And I'm perturbing around that limit, the limit of the ideal gas. This means practically that one basic requirement is that the typical scale on which my interactions decay compared to the length scale that defines my volume should be, this ratio should be definitely much, much smaller than 1. If this is not true, well, my expansion does not make any sense, right? Because practically it means that my interactions are practically long-ranged. All particles that are sitting in that volume see each other very efficiently. Okay, so this requirement is a requirement of short-range interactions.
Sorry.
Yes?
I don't get your last point about this.
Well, I'm saying if in order to have a perturbative expansion around the non-interacting limit, I must have short-range interactions. Why? Because if I have short-range interactions, the moment I add some interaction, only the particles that are very close will see each other, but particles that are very far apart will not see each other, and therefore efficiently I will have a small perturbation as compared to the non-interacting limit. If instead I have long-range interactions, the moment I add the interactions, all particles will interact with each other. Therefore, one basic requirement for the validity of the perturbative expansion is that interactions are short-ranged, and therefore that the typical scale on which interactions decay should be definitely much smaller than the physical size of my system. Okay? Should also be much smaller than the inverse, than the average, the instance of part. Yes?
I feel like your voice is getting smaller and
no, it's not.
I don't know. Maybe it's my equipment.
Yeah, well, I don't know. I mean, it could be. Anyway, if I do this, then it's clear that this second term here is much smaller than the first.
Sorry, Professor.
Yes.
I think that the second term of the left part should be square of the I mean the second term of the left part of the
Mi scusi, mi può
equation.
richiamare fra un po' che sto lavorando adesso? Sto benissimo, la ringrazio. Ok, sto da Dio, veramente bene. Grazie tanto. Scusa, sorry guys, I had a phone call and I had to answer. So what was the question again?
Yeah, I have a question about I think that the second term of the left side of the equations should be square of the all the thing in the brackets.
Absolutely. You're right. Certainly. Yeah, thank you. It was a mistake,
Yes.
certainly. Thanks. Anyway, you agree that this term has an extra power of this small parameter as compared to this one, and therefore it can be neglected.
Yes.
This means that, but this term comes from this one. And therefore this means that this term can be neglected as compared to this one. Okay? In other words, this means that this is approximately n times n minus 1 divided by 2 integral dq over v vq squared. Because the other term is an extra, as an extra smallness.
Professor?
Yes?
Is this, I mean, this approach of actually the interacting classical gases, is this approach exactly like opposite of the one we take in mean field theory? Because I think I remember when you said
Yeah, absolutely. Is the opposite. Yes. It's a perturbative expansion. So I'm not assuming that the particles are, seeing a lot of other particles around, are interacting with everybody else. That would be the case for long-range interactions. What I'm doing here is I'm assuming that there's a few interaction only with neighborhoods. Okay, so you're right. It's kind of the opposite of mean field theory.
I mean, which cases is this working? I mean, and the mean field theory. So
well, mean field theory, as I told you, is working with high dimensions. For lattice models in high dimensions would be working for long-range interactions. This expansion should be working for short-range interactions. And it is an expansion at low densities for a gas. Okay? Low density, short-range interactions. Okay? All right, so now let me try to wrap up what we've done up to now. What we discovered up to now essentially is that the free energy F naught in this second order cumulant expansion can be written as follows. 2V integral dq v q minus beta over 2 dq v squared of q plus this. Okay? This is what we have discovered up to now. Now, the point is the following. If you would go on with the next order of the cumulant expansion, which is u cube, so you will have u cube naught minus, I think it's 3 times u naught u squared naught minus plus u naught cube. etc., etc., what you would discover,
Sorry, Professor.
yes,
Is it plus or minus beta over 2?
is minus. I think it's correct. So if you would go on, you would discover that this is what? This will, at the end of the day, lead you to some to something proportional to integral dq v cube of q minus 3 times integral dq vq integral dq vq squared plus integral dq vq. Oh no, this is not squared. Squared. Just a second.
Professor,
Yes,
in
yes.
the free energy expansion, shouldn't there be beta in the first term and beta squared over 2?
No, because if I put a beta here, beta squared, but I'm dividing everything by beta,
Oh, I
and
see.
therefore there shouldn't be. Okay?
Mm.
So what I'm trying to say here is that if you do the same calculation as before, you will also get for this third cumulant that all these terms here are actually an extra power of the ratio L over small l over big L. And therefore only this one will remain. And this is going to be true for the third order, for the fourth order, and so on and so forth. So in other words, if you would generalize this calculation, you would discover this. I invite you to think about this generalization if you want to try, for example, to see what happens for the third order. You will find the following, that this is equal to minus n times n minus 1 divided by 2, and then you have sum over n from 1 to plus infinity. This is, I'm resumming the entire cumulant expansion, minus beta to the n over n factorial, that's integral dq over v, vn of q. If you can easily check by multiplying by beta here that the first two terms of this expansion coincide with the first two terms we wrote down up there. And the characteristic of this expansion is that at each order, it contains only powers of V. Okay? So this is going to be the entire cumulant expansion for my system. If I go all the way to infinite order, it requires some thinking to get to this, but it's not hard. I mean, the logic is the same as the one I've shown you before. You just have to neglect to realize that this extra term that contains smaller powers of V is actually subleading as compared to this one that contains the correct power. Anyway, this one can be rewritten as follows: is beta f naught minus n times n minus 1 divided by 2 integral dq over v times sum over n from 1 to plus infinity minus beta to the n factorial p n q. And this is equal to what? Well, this sum, I know how to do it. It's just an exponential. So this is beta f naught minus n times n minus 1 divided by 2 integral dq over v of e to the minus beta vq minus 1. The -1 counts because this summation starts from 1 and not from 0. So this is my free energy. Okay? Now, since this is my free energy, let's use it. Let's, for example, compute the pressure using this free energy.
Professor,
Yes,
it's not F, right, but beta F.
yes. Okay, let's compute the pressure, which is minus dF dV. And this is minus n times n minus 1 divided by 2v squared times 1 over beta integral dq e to the minus beta vq minus 1. In other words, this is nkt, nk Boltzmann T divided by V minus, if n is large, n minus 1 is roughly n, so I can write it as n squared divided by 2v squared kBt, and then I have this integral dq e to the minus beta vq minus 1. And therefore, if I put things together, I get that P over kBt is equal to n minus 1 V times 1 minus n over V times integral dq.
Professor,
Yes,
how do you get NKBT there?
how do I get nkBt?
Yes,
This one?
yes.
Well, this is just a derivative of the non-interacting free energy. It's a calculation that we have already done. You remember when we calculated the partition function using the canonical ensemble. So what did we do? We did exactly this, right?
I see it now.
Okay, good, excellent. Times e to the minus beta vq minus 1. So I can think of this as n over v times 1 minus n over v times b2 of t, where b2 of t is nothing but this. And now you see something interesting. By this calculation, we have obtained a very interesting correction to the equation of state, because it's a correction to the equation of state. So the equation of state for the ideal gas can be written as P over kBt equal to N over V. You agree? And now here I contain a correction to the equation of state, which is of second order in the density, is next order in the density. It's as if I'm expanding in powers of the density. It's not a dimensionless parameter. So of course here, what stays here should be dimensionless. And if you think for a second, it is going to be dimensionless because there is going to be a length scale that pops up in this integral B2 of t. But anyway, I mean, roughly speaking, you see that in spirit is an expansion in the density. So when the density is very, very small, I can neglect this second term, and I'm left only with the equation of state with the ideal gas, as I told you many, many times in this course. And instead, when the density starts becoming larger, I will get corrections to the rho going to 0 limit that are subleading, okay? And depend on this coefficient. This is called the second virial coefficient. Of course, I mean, this is an expansion in the density essentially, and therefore it's going to have some next order terms. This is just a first order correction. If you start increasing the density, you will have a next order that essentially contains all the diagrams that we have been neglecting. Oh, sorry, all the terms that we have been neglecting. So where is it? So it's going to contain this one and the ones that we neglected at third order, and so on and so forth. All those terms are going to contain corrections to this expansion that are going to be higher powers of n over v times some appropriate length scale to the power d.
Professor,
okay? Yes.
What did you write the second virial?
Second virial coefficient.
Oh.
All right.
And you also said that this correction n over v times b2 should be dimensionless, right?
Yeah. I mean, of course, n over v times b2 should be dimensionless. So b2, if you think for a second, as the dimensions of a volume, right? Because it contains an integral. This is dimensionless. But here there is an integral over dq. So overall, from this integral, we'll get a length scale. Let's call it, I don't know, L tilde to the power d. And therefore, everything is going, this correction is going to be, of course, dimensionless. But what I'm trying to say is that apart from this detail, in spirit, this is an expansion in the density. So this length scale is going just to set a scale to determine what it means to be small density or high density, but overall is an expansion in the density. Okay?
But in this case, we are discussing about the low density gases, right?
Yes. So this is the first correction to an infinitely low density gas. Okay?
To the what? Infinitely low density?
Infinitely low density gas.
Oh, I'm sorry, I don't quite understand the term.
It's the first correction to the limit for the density that goes to 0. So the limit for super low density is the ideal gas. And this is the first correction to the ideal gas.
Ah, I see.
Okay. And now we will have the task to compute the next corrections.
Okay.
But in order to compute the next corrections, is much better, rather than using this cumulative expansion, to use another technique that is called the cluster expansion. So this is what we are going to do next time. It's much more complicated than this. So if you found this complicated, I invite you, since you have a few days, well, the next lecture is going to be on Monday. But since you have a few days ahead of the next lecture, take your time to digest a bit this cluster expansion, because the next one is a bit more cumbersome, okay?
Yes. Yeah.
Okay, guys.
What does it mean by second virial coefficient?
To be honest with you, I have no idea. I mean, there is something called a virial expansion, but I don't remember at the moment. I apologize. I will give you the answer next time.
Okay, thank you, Professor.
No problem. Any other question? Okay, guys. So I hope next time I will feel a bit better than today. Today was really hard for me to teach.
Next will be the cluster expansion, right?
Yeah, next one is going to be the cluster expansion, and it's going to be on Monday.
And
Okay.
I mean, I think I saw the materials on cluster expansion. It's full of diagrams. So will we study the diagrams?
Yeah, we will study the diagrams.
Okay. Thank you.
You will enjoy yourself with the diagrams. Don't worry. Okay, guys. So I'll see you next on Monday. Okay.
Yes.
See
Goodbye,
you.
Bye,
Professor.
Professor.
Bye bye. Bye bye.